Alright, so chapter review problems here for chapter 6. Starting out with number 7, you said?
Yeah.
So we have a definite integral from 0 to pi over 4 of e to the tangent x, secant squared x, dx. Alright, so ultimately here, if this is not a known derivative, which it clearly isn't, we need to let u be something that would differentiate to be something else that's here in this integrand. And I would hope it'd be fairly obvious at this point that tangent x should be our u. Because what's the u then? Secant squared. Secant squared x dx. Which ultimately would allow us to rewrite this integral as e to the u du then, wouldn't it? Tangent's taken care of with the u. Secant squared x dx is straight up du. No multipliers or anything to worry about. And what's the antiderivative of e to the u? Nope. It's e to the u. It's its own derivative. Therefore, it's its own antiderivative. And again, we don't put numbers on there because these are u values we have at this point. So if we change it finally to e to the tangent x, put in 0 and pi over 4. We put tangent pi over 4, that equals 1. That's where sine and cosine are equal. So ultimately it'd be e to the 1 then, minus tangent of 0 is 0. So e to the 0, so it'll just be e minus 1. And that'll do it. Questions on anything on that one? Okay, what else? 5, we have 0 to pi over 2 this time. Got 5 sine to the 3 halves x cosine x dx. So again, that's clearly not a known derivative, but if we let u equal sine x, then du would be cosine x dx, which would be very close to all the other stuff that I have besides the sine x that I just made into a u. And so ultimately, keep in mind again that first part, sine to the 3 halves x, could be replaced by u to the 3 halves now.
Wait, I thought, how come on that quiz it said, like, sine squared x is not equal to sine x?
That's not what it said. It said that the ln squared x is not equal to ln x squared.
Oh.
If I have sine squared or ln squared, that means
So you
this actually, this does not equal, this does equal. This is actually ln x all squared. Those two are the same that I arrowed, but the two next to each other are not.
Oh.
That's the argument is squared on this one. This one, ln x is all squared.
Okay.
So, again, no this way, yes this way. So with that said, keep in mind that we've already replaced this with our u. So we ultimately have a 5 and then a cosine x dx to get rid of. Well, we have a cosine x dx, so if we wanted 5 cosine x dx, couldn't we just go 5 du equals 5 cosine x dx, multiply both sides by 5? So if I did that, I'd have 5 out here, du here, put our 5 out because it's constant. And then if I anti-differentiate, if I go u to the 3 halves, if I add 1 to that, it's u to the 5 halves. So u to the 5 halves divided by 5 halves would be times 2/5, same thing. Still have a 5 out in front. So anti-differentiate at that point. And then from there, go ahead and plug in our u, which is sine x. And we're going 0 to pi over 2.
You multiply that by 5.
You can. I generally leave it out till the end though. I'd get the answer and then multiply the whole result by 5. Just to make sure we're clear on where the parentheses are and we don't miss multiplying it by the whole thing. So I'd probably just leave it out to the very end. Ultimately, then in this case, we're going to have a pi over 2 in here. Sine of pi over 2 is 1. So 1 to the 5 halves is 1. So we get 2/5 ultimately. And sine of 0 is 0, so that part would be 0. So final answer would be 5 times 2/5, which would be 2. That'll do it. Questions on any part of that one? What else? Review exercises. And number 9, we have cosine x on top. We have 2 minus sine x on the bottom. And at this point, we need to make a choice as to which one we want to let u. Seen before that if we let that be u, that would probably be the better choice because ultimately we'd have a u on the bottom, and then we'd have straight up cosine x dx here on top to get rid of. Which if we differentiate here, we're going to get negative cosine x dx, which is close. But ultimately, if we made the divide by -1, we'd get cosine x dx on the right, and that'd be equal to negative du. So then our substitution would look like u here, du here, negative out in front. So ultimately it would be negative ln of absolute value of u plus c. And again, our u is 2 minus sine x. We'll do it. And again, if you have time, you're done, and you got time left over, every one of these can be checked because you can do what? Differentiate this. You differentiate that, you better get back to what you started with. True? Like I said, you may not want to do that with every problem depending on how much time you have left over at the end though. I mean, if you got time left over, I wouldn't waste any of it until I've done all the checks. What else? Cody? 13, we got tangent of ln y over y. And ultimately, again, our u here, I would suggest using ln y because ultimately our du is going to be 1 over y dy, which is related to the other stuff. So with that, we're going to have just a simple tangent u du. Ln y is u. The 1 over y dy part is the du. Now, what's the problem that we have with tangent here? It's not a known derivative, is it? So that means we've got to substitute again, and we've seen this substitution. We've done this one before. We write it as sine u over cosine u du, and we let our w equal cosine u. Our dw would equal negative sine u du. So we replace negative dw. We could replace our sine u du in that integral. So with that, the new integral here then would be w on the bottom, negative 1 and dw here. We're replacing sine u du with negative dw. So here's your negative, here's your dw. U is, or w that is cosine u. And so ultimately we get negative natural log of absolute value of w plus c. And from there, substitute back twice and we'll have what we need. So negative natural log of absolute value of cosine u plus c. And then finally negative natural log of cosine of ln y plus c. And that would do it. Alright, just to decide at this point here, remember you have, I gave you on the worksheets that I gave you, which was all substitution problems, I gave you 3 through 54 by 3s. So that means they're still available to practice on. 1, 2, 4, 5, 7, 8, so on. Okay. These problems right here with just doing the substitution, you know, this is like learning algebra. You need to practice. Okay. So if you did a bunch of these last night and got them all wrong, okay, you need to practice. You know. So like I said, there's lots more problems. And in this part, I didn't assign all these either. There's more right here that you can practice on too. So like I said, this has got to get to a point where it's like riding a bike. This should be, you know, a piece of cake for us very soon, if not by tomorrow. Okay? So if you need more practice, there's tons of problems to practice on, but you just need to start seeing what are we going to let u equal because of this, that, or the other thing. You know, you've got to let it be something that's going to give us something that'll cancel out the other stuff that we had that we didn't make u. There's going to be the du element there. So like I said, in here, you know, as soon as you see the ln y and you got a y on the bottom dy, you know, should be an obvious substitution for us because we know that the du for this would be 1 over y dy. Okay, so those are the patterns that we need to start looking for. What else? Jeff?
17.
That should not have been on the list.
Oh,
Sure that was on the list?
oh, it's through 15. Sorry.
Yeah, safe. That's we'll learn that in BC. Well, some of you will learn it college next year. Connie?
46.
46 on our Newton's law of cooling. We got T and T sub S, T sub 0 minus T sub S, e to the negative KT. Okay. So the issue we have this time is that we have an apple pie and a deep dish apple pie, no less, which is important, obviously, to the problem. The internal temperature is 220 when it's removed from the oven, and it's set out on a breezy porch, which is 40 degrees, which ultimately is our T sub S, surrounding temperature. Our initial temperature here is 220 for this particular pie. And ultimately the question is, this is 15 minutes later the pie's internal temperature is 180. So ultimately it got to the temperature was 180, that's our current temperature if you will. Goes from 220 to 180 in how many minutes? 15 minutes. And ultimately that first piece of information allows us to find K for this problem. True? So if we do the math, we get 180 minus 40 is 140. 220 minus 40 is 180. 15K. And if we divide, we get 14 over 8 would be 7/9, I guess. Either the negative 15K. Natural log both sides. Divide. So ultimately our natural log of 7/9 over negative 15 is going to be our K. So it'll be our K value in this problem. And then the other part here says how long did it take the pie to cool from there, keep in mind it says, to get to 70 degrees. Alright, so if we reset up our formula, fill in our blanks properly, and we want to know how long did it take to get to 70 degrees. So we want to know when it's 70 degrees would be the current temperature. Surrounding temperature is still 40. And the initial temperature this time is going to be 180 because remember it said from there. Okay, so after the 15 minutes in other words. So the temperature after the 15 minutes is 180. So we want to know how long it takes to get from 180 to 70. And we know that our natural log of 7/9 over negative 15 times T. Right, so from there it's just a matter of solving the equation just like we did the previous one. So let's see what we get. We get 30 divided by 140. So we'd have 3/14 on this side. This would be e to the ln 7/9 over 15t. And if we compose both sides with a natural log, we're going to get a natural log of 3/14 over here. Over here we're going to get the argument ln 7/9 over 15t. And from there it's just a division problem. So if we take our natural log of 3/14 and divide that by natural log of 7/9 divided by 15. We get our 91.943. And the units on this would be 91.943 what? Minutes. Spell it right. Questions? Well, in the scheme of things, is that a calculus problem? Ultimately, the setup was given, so did we do any calculus in this problem? Pre-calc problem, isn't it? The calculus of it is what that particular equation came from. And I remember I said before that the derivation of that from getting from the differential equation to the t equation is something that we're not responsible for in this class. We just need to be able to use the t equation as such. So.
I doubt it takes an hour and a half.
Doubt what?
I doubt it takes an hour and a half to cool.
You could go home and bake one and try it and see.
Well, yeah, it's deep dish, so.
It is deep dish. Well, it's not deep dish. It would obviously be clearly less.
40 degrees, I don't know if I got that.
You get pretty close to 40. You could run the experiment if you want to. Victor?
Are we going to memorize that equation?
Yes.
Yeah.
If that's on the non-calculator part, you need to know it. So put that on your list of things to do tonight. Actually, not till Friday, because it wouldn't. Tomorrow you can theoretically type it in your calculator. 40?
49.
49, got the age of a sample of charcoal, which is 90% of the carbon-14, has decayed. So ultimately, our model that we're going to use here is our continuous change model. And like I told you before, that sometimes, depending on what book, this book recommends using the continuous change model for radioactive decay. We could also use the half-life model, which is A times a half times T over half-life. So either one of these models is okay. Just like I said, since they showed us in the book to use the continuous change model, we use that one for so that we're all in agreement with the answer here. And so ultimately, we want to know when does this fossil goes from 1 to 0.1. So again, 90% of it's decayed. So it goes from 1 unit to 0.1 units. And if you do your e to the kt, the question is how long does that take? Well, what's our problem here? Two variables. Okay. So that means that we need to use some information about carbon-14 to figure out what K is, which ultimately is figured out by using the half-life. And in your book, you go back to page carbon-14 one. I don't know if they said it in this book.
Example 3 on page
232.
Know that?
Oh, there it is. Yep. So 5,700 years. There we are. It was in there somewhere.
That's just common knowledge. You should know that.
Yeah. So just for carbon-14, you don't have to know any others besides carbon-14. And you'd be surprised, some books actually give different numbers for that too. Some use 5730 and other numbers, but for our purposes, for the time being, we'll use 5,700. And I can tell you right now, on the AP test, you're not going to have memorized that 5,700 is the half-life of carbon-14. Okay. So for our purposes, between now and the end, though, we'll just use 5,700 every time. So that means that our natural log of a half equals 5,700K. So ultimately, we'd have ln of a half. Half over 5,700 is our K.
Where'd you get a half?
So half-life goes from 1 to a half.
Oh, okay.
So it takes 5,700 years to go from 1 unit of it to a half a unit. So that allows us to find K. Once we have K solved for, then we can go back to our original here and have that, which the only thing now we need to know is T. So ultimately the answer is going to be ln of 0.1. Over here, ln of a half over 5,700 T. And if we divide, let's see, ln 0.5 divided by 5,700. And we get 18,934 and 99.99. And that's in years. Which again, hopefully from a common sense standpoint, that makes sense because again, it goes from 1 unit to a half a unit in 5,700 years. It would go from a half to a quarter, which is half of a half. So we'd lose another half of it in another 5,700 years, which would be 11,400 years. Okay. And then it would go from a half to an eighth, which is 0.125, in another 5,700 years. So at that point, we'd be looking at 1,600 some years. Okay. And then 0.125, it would go down to half of that, 1/16 is 0.0625. So it'd be somewhere in between those two half-lives, where we'd be. So more than 16,000, less than 20-some. We added another 5,700. What else?
I just got a question. So, let's say it was 80% carbon-14. Would that number just be 0.2 instead of 0.1?
Yep. If 80% was gone, right, then we'd have 0.2 left. If they said there was 80% still there, then it would be 0.8 in there then instead of 0.1. What else?
One.
On 51, we have another differential equation, and you notice that the differential equation is of the form that dy dt equals ky form. So we should expect that our equation that we find for this is going to be very similar to our continuous change model here, because we have something dl dt that's proportional to L. Okay? And ultimately, the variables in this case, the L is the light intensity here, that's in x feet, and beneath the ocean surface, blah, blah, blah. And so ultimately they ask us some questions here. To do that, we're going to need to find out what K is ultimately, or actually what the equation is here, the L equation. If we want to know something about the light intensity, we'll need an equation. So if we separate our variables and do our work as normal, we'd have 1 over L on the left, dl, negative K dt over here. So we'd have natural log of absolute value of L, negative kt plus c. And at this point, let's see what information they gave us if we were able to find our c value here. It says that as a diver from experience, you know that diving to 18 feet cuts the light intensity in half. Okay? And it says ultimately you cannot work without artificial light when the intensity falls below 1/10 of the surface value. And the question is about how deep could you expect to work without the artificial light. Okay? All right. So the ultimately here, if we have our equation and we ultimately finish our equation, we're going to wind up, we know, with L equals L sub 0 times e to the negative kt. Okay. All right. So in lieu of doing all that, let's just get to the result here at this point, because we know that kind of a differential equation always gives us the continuous change. All right. And so knowing that the light intensity is, I think they said, yeah, so 18 feet it gets cut in half, right? So ultimately if I do 1, if I consider the light intensity to be 1 at the surface, half would be, actually that's an x right there, so it would be negative k times 18. That would allow us to find the k in this problem. So again, our light intensity goes from 1 unit, whatever it may be, to half a unit, okay, in 18 feet. So knowing that, if we do natural log of a half, negative k times 18 over here, so it would be a natural log of a half over 18. Actually, it would be negative. We'll divide by negative 1, so divide by negative 18 if you will. So that being our k, then if our light intensity, putting that in as our k, we'd have ln of a half over 18 times x. So again, we're taking a negative k and putting it into negative k, if you will. So keep in mind this is actually a negative quantity here, because ln 1/2 is negative. Anything before 1 is a negative. And with that, we want to know, ultimately similar to what we just did in the other problem, we want to know when it goes from 1 to 1/10. So really it's the same equation as what we had just a minute ago, just a different k, isn't it? We want to go when it goes from 1 to 0.1. Okay. How deep do we have to be to get it to go from 1 to 0.1? And so ultimately our answer then would be natural log of 0.1 divided by natural log of a half over 18. That would be our x. So let's find out how deep that would have to be. So natural log of 0.1 divided by natural log of 0.5 divided by 18. And we get 59.795 feet. Is our x. That's gonna do it. So ultimately, one of the reasons why it's important too that we consider, ultimately we could have come up with the same result here if we would have finished this, just for time's sake though we won't. If we would have put in the light intensity to be 1 and the time to be 0. So again, they didn't tell us what the light intensity is at the 0 value of x, if you will. But if we just consider it to be 1, I mean everything's relative. So if we consider it to be 1, ultimately they ask us for a 1/10 of it. 1/10 of what? 1/10 of the original. You know, the original could have been 50 if we wanted it to be, but ultimately what would we have gotten? We would have gotten the same answer. It wouldn't matter, because ultimately we would divide. So remember, at this point, when we're at an equation like this, even if it was 50 and we put a 25 here, wouldn't this still be ln of 1/2 when we do our ln part? we'd have to divide by 50 to get to this point first. So ultimately, it really doesn't matter what we call the light intensity at the surface, if you will. So if we call it 1, that would be reasonable. Be the easiest way to do it, wouldn't it? Anything else on that one? What else? Huh?
What were the true and false for the, like, page?
64?
Yeah.
Is that the
47 was false, 48 was true.
Oh.
so you didn't watch the video?
What?
I was confused today.
You want the
So,
other
so you didn't watch the video?
I watched the one that, like, Friday.
Well, it was on the video.
Where's the video that we did yesterday?
If you're gone, you should definitely watch the video.
Oh, usually
Oh, yeah.
I do watch the video, but I didn't.
You want the
Okay, anything else on the review assignment before we move on to the practice quiz, practice test?
Ronnie, you got the rest of those? The answers? And it's
Tell her to watch the video.
Okay, watch the video.
Actually, the rest of the answers are they're on the paper already, aren't they?
Oh,
Multiple
yeah,
choice
they
are on
are.
the paper. Okay, let's take a look then at our practice quiz and test. Put up the answers here first. We had 1, 2, and 4 on. One, 2, and 4 on the quiz. Should have been D, C, and B.
Wait, time out. Wait, what?
Paper 6.
6, 4, 6, 6, practice quiz.
Okay.
So we got D, C, and B. So just check answers for the time being, and then we'll look solutions here in a minute. Here's I think we did 1 through 7 on this part, right? So there's 1 through 7. Take a minute to check your 1 through 7s. And then we had 11, 12, 13, 14. Nope, it's 11, 12, 13. Alright, let's start with the quiz first. Comes with 1, 2, or 4.
I just had a question.
Yep.
Are you always, like, on number 4, are you always, like, using a perk for, like, most of the compounded ones?
Are you talking about in the quiz?
Yeah, I'm just talking about, like, in general, like, when we get problems that involve compounding. Is it always going to be a perk, or?
Not necessarily. That's only if it's continuous compounding. Okay. So anything that's continuous change is y equals y sub 0 e to the kt. Okay. So that PERT business is only with money. So, but ultimately it's only if it's continuous change. If it's just exponential change, we use the normal y equals a times b to the x as our model. Okay. Again, if you're given a differential equation that's of that ky type, then ultimately that's always going to give you continuous change. Okay. Thing on quiz. 1, 2, or 4.
Wait, did you guys say 245?
E, C, B.
DCB?
Alright, how about test then? Stuff.
7.
Okay, at 7 we have separation of variables problem. We have dy dx equals cosine x through y squared. Y of pi is 5. So if we separate variables here, we're going to have 1 over y squared dy. We could bring the 3 over there with it as well. Back out of this thing. We could bring the 3 over there with it as well, but I would leave any constants on the right, and therefore we'd have 1/3 cosine x dx on this side. That's what I would do. I'd always leave the constants on the x side. Again, you don't have to, but if you had 3y squared here, then you'd have to deal with that over on this side, and I find it easier to leave it on the right. So with that, we'd get y to the negative 1 over negative 1. Over here, we'd get 1/3 sine x plus c. We anti-differentiate.
Separate that with the y when you multiply by y. So when
Oh, you know what? Darn it. You're right. Sorry. Let's change that. That should be y cubed over 3 then. There. That's better. Correct. Yeah, I forgot it was on the bottom. So just y squared, not 1 over y squared. So y squared dy, y cubed over 3 then would be our result. And then if we put in a 5 here, we get 5 cubed over 3 on this side. 1/3 times sine of pi plus c. Ultimately, c then would be 125/3. Sine of pi is 0. So with that, we'd have y cubed over 3. We'd have 1/3 sine x plus 125 over 3. And in solving for y here, we'd multiply by 3 first, which conveniently would get rid of all the fractions. And then if we take the cube root, sine x plus 125. And that would do it. Questions on that one? What else? Just for argument's sake, too, just make sure you don't get hit by a train and rewrite this as that. So what did someone do and then get hit by the algebra train?
Separate them and make that 5.
You can't separate a sum when you have a square root or a cube root or any root. If these were being multiplied, then you could separate them and do the individual parts. Or if they're being divided, okay, but not with addition and subtraction. You can't separate those two and make them two separate radicals. Okay, ultimately, because is radical 3 plus radical 4, does that equal radical 7? No. So therefore, by saying that, wouldn't that be doing the same thing as you did by doing this? So don't do that, nor that. All right, what else? Josh? Let's see, on 12 we have our equation that we're given here is v equals v sub 0 e to the negative k over m t. Alright, so ultimately this is a continuous change model of the sort that we've seen here. It says it's a 1,200 kilogram car, coasts to a stop from a speed of 20 meters per second. And the car's motion obeys this equation, and the k here is 80 kilograms per second, so that means that we can put that in right now if we want to. Put that in as 80 over m times t. Alright, so let's see if we can figure out here the part A here says about how far will the car coast before reaching a complete stop, and it says around to the nearest whole meter. Alright, so keep in mind here that with the given information here, with our velocity, our initial velocity here was 20, right? True? Alright, if our initial velocity is 20 and the car weighs 1,200, the time that it takes for that would be 20 seconds. Right? Alright. And ultimately the question is, what is that going to tell me if I have my v here? Because ultimately they've given us, it seems like they've given us all the variables, haven't they? Because I want you to take a look here, find page, flip back in your book to page Let's see. Page 336. There's a couple of results here that I want you to look at. That we didn't actually do a problem like this in our homework, and there won't be one on the test either. I'll tell you that. I want you to try it just so you can see another application. But ultimately, again, the culmination of that should be that, because we want to know when the velocity goes from 20 to 0. Okay? But really, in the scheme of things, that sentence isn't going to make perfect sense, is it? Okay? This might be close to 0 when we get done with it, but ultimately it's not going to be exactly 0. Okay? There's a couple other results, though, that come from this, and if you look at the bottom of page 336, if you look at where it says in exercise 31, you will show that the total distance coasted by a moving object encountering resistance proportional to its velocity, which is the case that we have here, is that distance traveled is v sub 0 m over k. And you would have had to do your reading to be able to find this. But the v sub 0 again is 20. The mass is 1200, and the k is 80. It said. Right. And so that distance here, if we do our 20, that is, times 1200. Divide that by 80, 300. And the units here are, is it meters? Can't remember.
Yeah.
Yeah, so 300 meters it would take. So that's how they got 300 in the first part of the answer.
What about that other part?
We ultimately don't need that for this particular problem. So the other one though that they give us, the other question that they give us is about how long will it take for the car's speed to drop to 5 seconds. Okay. All right. So ultimately, in that particular case, then we could use our v equation, the original v equation, because our v would go from 20 to 5, and then our negative 80 over 1200 t. Then the t would be the variable for the time it would take to go from 20 to 5. So that would be this model. The reason this model doesn't work is because if we put a 0 in here, we're not going to get it. We don't have any variables, do we? Right. So if you go from 20 to 0, that's why this particular equation doesn't work for that first question in terms of the distance traveled. Because ultimately, does this even have distance traveled in it? No. So that equation wouldn't work. But in this case, changes in velocity and how long that takes, knowing k, is something we can solve. So ultimately, we get a quarter over here. And we take the natural log of both sides, and we get negative 80 over 1200 t. So if we do that, do the math on that, divided by negative 80 over 1200, and we get 20.794 seconds t. All right. So like I said, you don't have to memorize. This equation. Like I said, it's just a different application I wanted you to look at. Like I said, in the part B problem, then we use the model as normal. In the part A problem, we need to use this other result. Right?
The one with no variables, where you get the 20 for t.
Yeah.
It took 20 seconds, didn't it?
Says the speed's 20 meters per second.
Oh, I thought it said it took. No, never mind. Okay. I guess there wasn't a 20 then.
So you could solve that.
Ultimately, the inlying problem though is when we divide by 20, we're gonna have 0. If we take the natural log of 0, the result is gonna be what?
Here.
Undefined, right? That's the problem with using that. And ultimately, we could get the time that it would take to stop, but the time really doesn't help us anyway either, does it? Because ultimately, we want to know the distance that it goes. So therefore, we have ultimately two different equations when we deal with this coasting speed. All right. What else? Yeah.
Do you remember
11, we have similar to the half-life one we had earlier. They already told us what k was, which was convenient, and we want to know what's the half-life. So ultimately, we just want to solve this for t. 1 in for y sub 0 and half in for y. So if we solve that, it's going to be natural log of a half divided by negative 1.2 equals t. Skipping some steps here because we've solved that equation several times now. So you can get a decimal for that, of course. It says nearest 0.001 years. And then how many years will it take to get to 98%? or for 98% to decay. So ultimately we need to solve the next 0.02, 1, e to the negative 1.2t. Solve that the same way. What else? Yep. Number 1, we have, it says use the fundamental theorem to evaluate. We have e to the x squared plus sine x dx. Alright, so the culmination of this is that if we were to try to substitute here, because we know that's not a known derivative, our du here would be 2x plus cosine x. But you'll notice in this case, is there any 2x plus cosine x along with our original integral? That what we're trying to substitute? Nope. So that really doesn't do much for us then, does it? And so if substitution doesn't work and it's not a known derivative, then we really only have one choice. Okay, our integral, remember again, if we're trying to anti-differentiate some equation, whatever it may be, if we can't find an antiderivative for it, okay, then we can always just rewrite it as a definite integral, and we usually use a dummy variable here, so e to the t squared plus sine t, and we go from 0 to x dt, and again, keep in mind they didn't give us an initial condition this time. Normally the initial condition, the x value is here, right? And the y value would be here plus whatever to make it go through that particular point. We don't have a initial condition here, so we really can use any a value that we so choose here and just put plus c on the end of it, because ultimately this would represent an antiderivative. And think about why, in this particular case, if we were to anti-differentiate this, we'd find the antiderivative. We'd put in x, we'd put in 0, and we'd ultimately get the antiderivative of this evaluated at x, which is just an antiderivative plus c then, isn't it? So hopefully that matches up with letter D. I believe that's what I said, right? Okay. So again, if you can't find an antiderivative for a particular function, you can always write it as an integral equation with, again, if there's an initial condition, then your a and c are going to be specific numbers. Okay. If there is no initial condition, then you can always go to 0. You can always use 0. Go to x, change your variables to a different variable. You can't use x here and x here because that wouldn't be correct. Okay. What else? Right.
Number 8.
8 wasn't on the list.
Didn't do.
1 through 7.
Oh.
13. On 13, we have a, this is the relative growth rate of a population of Brockton is 0.031. Its current population, p sub 0, is 56,800. And we want to write a differential equation for the population. If I were you, just for argument's sake, I'd put a star by this problem if I were you. Ultimately, that is going to be the differential equation because they told us that it's a relative growth rate, and relative growth rate means that the population is proportional to itself, if you will. And the k value here is going to be the relative growth rate. K is the relative growth rate, so that would be the differential equation. So for part 1, that is the result. Okay. And so from that, our next job is to find a formula for p in terms of t. So we have two choices. We could separate the variables and solve the differential equation with our solving steps, or we could recognize that the answer to this is just that, and that. And we know that the initial population is 56,800, and we know that k is 0.31, so wouldn't that do it? Again, if we had done the work, which wouldn't take a whole lot to do, see how that would play out, because again, the question is, do we have to memorize that? No, because you can always just derive it. So I'd have ln of absolute value of p. Over here I'd have 0.031 t plus c here. My initial condition is 56.8, so ln of 56.8 equals c. I'd have ln p 0.031t plus ln of 56.8. And if I compose both sides with e, and I do my 0.031t, and then my ln 56.8, ultimately that part right there is just your 56.8. So what do we wind up with if we did it the long way? Exactly the same. Alright, so like I memorize the fact that if you have the differential equation as such that it gives you the continuous change model every time, and just go to work and do very little work if you know that. Okay. Otherwise, you can solve the differential equation if you don't remember that. And good to go. So,
Why does it put a negative k?
when it's essentially when it would be decay. They told us it was if there was instead of relative growth rate, if it was population was decaying, it would be a negative 0.031.
Or if it's like a cold problem, then it's cold, that's negative, right? Maybe.
Right. Yep. Because that's always temperature decreasing. In the original form, the temperature is decreasing. We had one where the temperature increased, but ultimately the negative became a negative-negative situation and became positive. What else?